next topic is effect of frequency and supply voltage and iron losses. So iron losses are divided into two types. One is hysteresis losses and eddy current losses. Hysteresis loss and eddy current losses. Hysteresis loss is equal to neta B max power x FV, where x is equal to 1.6 for silicon steel. Eddy current loss is equal to K into B max square, F square, T square. So neta is called the Steinmetz coefficient, B max is the maximum flux density, F is the frequency of the supply, and V is the volume of the core. And K is a constant, B max is the maximum flux density, F is the frequency of the supply, and T is the thickness of laminations. See, this iron losses depends on voltage. The induced EMF of a single phase transformer is 4.44 into B max into AN into F into N. If it is a N number of turns, it is a primary induced EMF. If it is a N2 number of turns, that is the secondary induced EMF. So once design is over, net cross sectional area of the core is constant, number of turns on the primary winding is constant, and 4.44 in the EMF equation is also constant. B max is directly proportional to E1 divided by F, that is directly proportional to approximately V1 divided by F, where V is called the supply voltage. So this is a core type of transformer I am trying here, and I am wound the winding on one limb. This is primary winding and another one is the secondary winding. So yeah, primary winding has N1 number of turns, secondary winding has N2 number of turns. I am giving a sinusoidal voltage. So B max is directly proportional to V1 divided by F. So if a B max is constant, that means the V by F ratio is constant. If a V by F ratio is constant, then B max is also constant. Then hysteresis loss is directly proportional to F, and eddy current losses is directly proportional to F square. And hysteresis loss is equal to now AF, and eddy current losses is equal to B into F square. And the total iron losses is equal to, it is a summation of hysteresis losses and eddy current losses, AF plus BF square, and iron losses divided by F, that should be equal to A plus B into F. So if you draw the curve between, so Wi by F versus frequency, and at the frequency value is 0, Wi by F is equal to A, so it is a constant one. The length of this line is A. After that, it should be in the form of Y is equal to Mx plus C. So this is a variation, the theta B into F. So that is the one condition. The case 1, in a case 1, V by F ratio is constant. V by F ratio is constant. In a case 2, voltage is varied but frequency is constant. What will happen? So if voltage is varies and the frequency is constant, anyway V by F ratio is not equal to before and after voltage is varied, and the hysteresis loss is directly proportional to V1 divided by F whole power 1.6. Why? Because B max is directly proportional to V by F, and V1 whole power 1.6. From this, hysteresis loss is directly proportional to V power 1.6 because the frequency is constant. And coming to the eddy current losses is directly proportional to V max square, that is V by F whole square. Anyway, frequency is constant. The eddy current losses is directly proportional to V square. Now the iron loss is equal to V power 1.6 plus V square. That means A into V power 1.6 and B into V square. In a case 3 voltage is constant and the frequency is varied. In case 3, voltage is constant and frequency is varied. Hysteresis loss is directly proportional to V by F whole power 1.6. That 1.6 for the silicon steel. If a V is constant and hysteresis loss is directly proportional to F power minus 1.6. The eddy current losses is directly proportional to V by F whole square, B max square, F square. And the frequency value is varied and the frequency will be cancelled, and the eddy current loss is directly proportional to V square, and here the voltage is constant, the eddy current losses is constant. When the frequency is varied and voltage is constant, the eddy current losses is constant. Okay, and if in case 4 voltage is varied and the frequency is also varied, but V by F ratio is not constant, then hysteresis loss is directly proportional to V power 1.6 minus F power 1.6, and eddy current loss is directly proportional to V square. Eddy current loss is directly proportional to V square. The V square, V by F whole square into F square, and these two are cancelled, and eddy current loss is directly proportional to V square. Now coming to one problem. A 1 kilovolts by 2 kilovolts transformer has 750 watts hysteresis loss. So hysteresis loss is equal to 750 watts, and the eddy current losses for this problem is 250 watts, and so V1 is 1 kilovolt on primary side, and this is called the E1 and E2, and V1 is approximately equal to E1, and the apply voltage is doubled and frequency is offed. So the V2 is equal to 2V1, F1 is equal to F, and F2 is equal to F divided by 2. Check that V by F ratio is constant or not. V1 by F1 is equal to 1 divided by F, but V2 by F2 is equal to 2V1 divided by F divided by 2. That should be equal to 4V1 divided by F. So V1 by F1 should not be equal to V2 by F2. V1 by F1 is equal to V2 by F2, but here it is not equal. Directly substitution. Hysteresis losses is directly proportional to V1 by 1.6 into F, and the eddy current losses is directly proportional to V square. That means V by F whole square into F square, and the hysteresis loss 1 divided by hysteresis loss 2, V1 power 1.6 divided by V2 power 1.6, F2 divided by F1 whole power 1.6 into F1 divided by F2, and the eddy current losses divided by eddy current losses 2, eddy current losses 2 is equal to V1 by V2 whole square into F2 by F1 whole square into F1 by F2 whole square. Now we know that V2 is equal to 2V1 and F2 is equal to 0.5 into V1. Hysteresis losses to 750 divided by WH2 is equal to 0.5 whole power on 0.6 into 0.5 whole power on 0.6 into 2, and here 250 divided by PE2 is equal to 0.5 whole square into 0.5 whole square into 2 square. Then finally hysteresis loss 2 is equal to 3446.095 watts and the eddy current losses is equal to 1000 watts. That means hysteresis loss WH2 and WA2, that means PE2 and WA2 both are same, that should be equal to 1000 watts. Now the total losses is equal to PH2 plus PE2, so 4446.095 watts. The eddy current losses are equal to, the eddy current losses is directly proportional to V square. So coming to the second problem, if V by F ratio is constant, see a single phase transformer has hysteresis losses is equal to 300 watts and eddy current loss is equal to 400 watts. So with a voltages of 1 kV divided by, that is 2 kV, having a frequency of 50 Hertz. Now the voltage of single phase transformer is doubled and frequency is also doubled. Find the hysteresis loss and eddy current losses. So what is the equation for this one? The hysteresis loss is directly proportional to F and the eddy current loss is directly proportional to F square. Check that V by F ratio is constant or not. V1 is equal to 1 kilovolts, F is equal to 50 Hertz, that is F1. The V2 is equal to 2 kilovolts and F2 is equal to 100 Hertz. See, now the voltage of single phase transformer is doubled and the frequency is also doubled. Check that V by F ratio, it is 1 by 50, that means 1000 divided by 50, and V2 by F2 is also 2000 by 100, so this is 20 I think, so here also 20. The V by F ratio is constant, then hysteresis loss 1 divided by hysteresis loss 2 is equal to F1 divided by F2. The hysteresis loss 1 for this problem is 300. 300 divided by hysteresis loss 2 is equal to F1 is 50 and F2 is 100. Then the hysteresis loss 2 is 600 watts. And coming to the eddy current losses is directly proportional to F square We2 by We1 is equal to F2 divided by F1 whole square, and the We2, what is the We2 value? We have to find out. The We1 is 400, so 100 divided by 50 whole square. The eddy current losses is now 4 times, right? 400 into 4, that should be equal to 1600 watts. So hysteresis losses 2 is 600 and hysteresis losses 2 is 200 and eddy current losses is 1600 for this problem. So coming to the next problem, a single phase 220 volts by 115 volts transformer has hysteresis loss of 300 watts and eddy current loss of 400 watts with the frequency of 50 Hz. Now the transformer is to be operated at 160 volts 50 Hz. What is the new value of hysteresis loss and eddy current losses? See, this is Z1 and E2. V1 is 220 volts and hysteresis loss 1 is equal to 300 watts and eddy current loss 1 is equal to 400 watts. The frequency of 1 is equal to 50 Hz. And now it will be operated as at 160 volts, as the input frequency is 160. Now what is the hysteresis loss 2 and eddy current losses 2? The frequency is also same. Frequency is also same. For this, F2 is equal to F1. Then hysteresis losses is directly proportional to V power 1.6. And eddy current loss is directly proportional to V square. WH2 divided by WH1 is equal to V2 by V1 whole power 1.6. WH2 divided by 300 is equal to, that V2 is 160 and V1 is 220. Yes, V1 is 220 whole power 1.6. What is the value of so 160 power 1.6 divided by 220 power 1.6 into 300. So now from this I calculated hysteresis losses as 180.234 watts. And coming to here, eddy current losses 2 divided by eddy current losses 1 is equal to V2 by V1 whole square. And eddy current losses 2 divided by 400. The V2 value is 160 divided by 220 whole square. 160 square divided by 220 square into 400. So eddy current loss is 400, right? Okay. Now the eddy current losses 2 is equal to 211.57 watts. See, in the case one, first problem, the V by F ratio is not constant, and then we are calculating with the frequency variation. Coming to the second problem, if V by F ratio is constant, so what is the hysteresis losses and eddy current losses? And coming to the third problem, and what is the frequency is same, S frequency is same, what is the mean by hysteresis losses and eddy current losses?